Hello and welcome to our entry for the computational challenge. For task 1, we reproduce a linear correlation described by Kepler's third law in Python and Excel. To plot the orbits of the planets in task 2, we use the polar equation of an ellipse for 1000 linearly spaced angles, plotting the inner planets and the outer planets in separate graphs. For task 3, we use the linearly spaced values of time, converting each value of time to the polar orbital angle. For optimization, our program calculates the coordinates of every planet at each point in time before starting the animation. For task 4, we calculated the x and y coordinates in the same way and transformed them to x, y, and z coordinates using the orbital inclination angle. For task 5, we coded Simpson's rule to numerically evaluate the integral. We used Simpson's rule together with Simpson's 3/8 rule to approximate the integral for when there were an odd number of strips. We plotted the graph of orbital angle against time, in addition to creating a conversion algorithm for both Mercury and Pluto. For task 6, we plotted the line segment between any two planets at each point in time for n orbits. For the final task, we updated all of our models so that any planet could be chosen as the center by subtracting the coordinates of the center planet relative to the Sun from the coordinates of all the other planets.
We then integrated the 2D and 3D animations of task 7 into a PyQt application. It shows the animated orbits of the planets as well as orbital parameters such as linear velocity and distance from the Sun. We derived the formula for linear velocity by equating the equation for total energy of a planet to the sum of the kinetic and potential energy of the planet. We fully integrated 3 additional planetary systems, the Tau Ceti, the HD 209134 system, and the Proxima Centauri system using enums in Python. The orbits are animated for any center planet or star, which can easily be manipulated here. We also animated the spirographs, allowing the user to choose the animation speed and any pair of planets in one of the available star systems. Lastly, we wrote a paper describing the mathematical foundation of our models and modeling assumptions. We also considered how we reduced floating point errors using the decimal module. Thank you very much for listening. We hope you liked our project.